Unit 6 is all about Lewis structures. Structures by which one can draw chemical compounds showing all the valence electrons as either bonds, lines, or lone pairs, these pairs of dots. In this particular video, I want to introduce you all to Lewis structures, and we'll also discuss the Octet Rule and summarize the bonding of some period 2 elements. Okay. Lewis structures were developed by the scientists Gilbert and Lewis in 1916. And this is his theory of chemical bonding. It hinges on the understanding of what's called the Octet Rule. And that says that an atom will lose or gain electrons to get to a noble gas configuration. If we look at the periodic table, particularly first for hydrogen, hydrogen is in period 1, and there's only one orbital in that period, and that's the 1s orbital. For the 1s orbital to be completely filled, you need 2 electrons. Therefore, hydrogen, when it has a filled valence shell, will have 2 electrons. But when you get to the period 2 elements, for instance, carbon, okay, there are 2 orbitals, or 2 types of orbitals, the 2s and the 2p, but there are 3 2p orbitals. Hence, maybe I could zoom out. If you look at period 2 needs 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8, to have a filled valence shell. Let's skip down to period 4, but realize that these d orbitals for the transition metals, those start in the energy level 3. So still, even if we take an element like bromine to have a filled valence shell will need 8 electrons because the valence shell is valence shell n equals 4. 1, 2, we don't count these electrons because these are in the 3rd energy level. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so to have a filled 4 shell, you need 8 electrons. Okay. So that is the noble gas configuration. And let me give you a couple of examples. For instance, oh, by the way, let me just put here, what you're trying to really attain is a filled valence shell. And in most cases, it's going to be 8 electrons. Let us take carbon. Carbon has a Lewis dot symbol like that. Remember Lewis dot symbols? Lewis dot symbol for just the element carbon. What we see here is that those dots represent the 4 valence electrons. And it needs 4 more to satisfy the octet rule. Okay, how does carbon accomplish that? One way, there are many ways actually, but one way carbon grabs those 4 electrons is by making bonds. And we're going to look at also hydrogen. So hydrogen has one valence electron, so it needs one more to fill its 2s orbital. Hydrogen needs 2 electrons to fill its valence shell, because its valence shell is actually n equals 1. N equals 1, the first row. Well, that works out well, because if we take 4 of these hydrogen atoms, and we take 1 of this carbon atom, we could combine to make bonds and also satisfy the octet rule for carbon. So yes, hydrogen doesn't satisfy the octet rule because you can't fit 8 electrons in the n equals 1 shell. You can only fit 2. But what do we accomplish here? By sharing electrons, so these are covalent bonds. You are sharing electrons, or the 2 atoms are sharing electrons, a pair of electrons. That's different than ionic, right? This is not ionic. We know that as the transfer of electrons to get ions. For instance, sodium chloride, the sodium 1 valence electron is given up to chlorine, which wants to gain an electron to have its octet shell filled. So this is that, ionic bonding. This is covalent bonding. Okay. What do we satisfy with this? Again, carbon satisfies the octet rule. So let me draw it down here. There's a shorthand that if you have a bond and it's made of 2 electrons, you could indicate that with a line. So we have here carbon with 4 hydrogens. This is the Lewis structure of CH4. And a Lewis structure has to show all the valence electrons. If you're asked to draw the Lewis structure of a molecule and you're given the molecular formula, you have to show all the valence electrons. So if we take a look at CH4, there are 4 valence electrons for carbon. That will always be the case, right? For neutral carbon, I should say. Plus, you have 4 hydrogens that each have 1 valence electron. And that equals, what does that equal? 4 plus 4, that equals 8. Okay. It's just a coincidence that it's 8. Obviously, we're going to have other molecules that have more than 8 valence electrons. But literally, you could count them because you're counting 1, 2, 3, 4, 5, 6, 7, 8. So practice counting valence electrons. Okay. Let me just make sure I have everything here. Oh. Let me just emphasize again, for the Lewis structure, Lewis structures show all valence electrons. Okay. Let us take a look at nitrogen. Let's try one more example before we make a table of valence electrons and bonds. Nitrogen here has how many valence electrons? 1, 2, 3, 4, 5. If you're having trouble remembering the valence electrons or understanding where I'm getting these from, we could always draw the electron configuration. You see how concepts that you've learned in past units are going to be still important that you understand to understand the new material. One of them is electron configuration. Because literally, we will see the valence electrons. You have to know where the valence electrons are and how they behave once you put them in the context of a molecule. 1s2, 2s2, 2p3. Your shell, or your valence shell, is n equals 2. And you just count how many electrons are in the valence shell. Therefore, symbol for therefore are these 3 dots in a triangle. Therefore, nitrogen has blank valence electrons. There are 5. And we have the electron configuration. What if we have the Lewis dot symbol? It's also important to make sure these terms are very clear in your head, because you don't want to answer a problem on an exam like answering the electron configuration when they really wanted the Lewis dot symbol. So you have to know, what do they mean by Lewis dot symbol? It's the notation where you show the valence electrons as dots. Okay, remember that? And it doesn't matter where you put the pair. Okay, just put it, there should be 1 pair and then 3 electrons that are separated, 3 single electrons. That's convention, but also it's going to help us with the Lewis structures. Because if I draw a molecule with a central nitrogen, the simplest Lewis structure that I could draw with nitrogen is NH3. Let's practice. Count the number of valence electrons. There are 5 for nitrogen. There are 3 hydrogens that each give 1 valence electron. So this is also 8. The reason why we're getting 8 all the time is that the only atom in our structures that have to satisfy the octet rule is the central atom, and there's only one of those. Carbon needs 8 valence electrons. Nitrogen needs 8 valence electrons. We could accomplish that by adding 3 hydrogens. So the Lewis structure of NH3 is this, N. And now I'm going to go ahead and start using lines to indicate the shared pair of electrons. These are bonds. Okay, we have that. And don't forget there's 2 electrons on top. That is called a lone pair. It's not involved in bonding. So some textbooks call these a non-bonding pair. It is still part of the valence count. So when you count, counting is going to be very important. For this nitrogen, you're counting valence electrons. Yes, I understand that 5 valence electrons came from nitrogen and 3 valence electrons came from hydrogen. They're not being transferred, they're being shared. So the electrons here, you could count them for both the hydrogen and the nitrogen, meaning that this hydrogen here has 2 valence electrons. It's filling its valence shell, actually. And this nitrogen here has 8. So when you're in a compound, I know that we're double counting, basically, these 2 electrons. Because these 2 electrons do count as part of the octet rule for nitrogen, but they also count as the 2 valence electrons for hydrogen. The thing is, when you count the number of valence electrons in the compound from the molecular formula or the chemical formula, just add up the valence electrons for each atom. When you count valence electrons on the compound itself, what you're really doing is you're trying to see if the atoms satisfy the octet rule. So again, the counting is important. You're going to count it this way. Around nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. You count every single electron that you see. When you have a line, you should be seeing 2 electrons. When you have a lone pair, you should be seeing 2 electrons. The bottom line is that N satisfies octet rule. That is our main conclusion when we have the Lewis structure of NH3. Okay, let me just make sure before I move on to the next page, since looking at covalent bonds. Okay, yep. We've looked at bonding for carbon, and we've looked at bonding for nitrogen. Okay, we're going to keep going down the period 2, and we're going to look at bonding of oxygen and fluorine as well. But now we're going to start putting this into a table, try to organize our thoughts in something that we can study fairly easily. So we're going to have several columns on this table. The first column is going to be the Lewis dot symbol. Oh, by the way, later on in the unit, we're going to talk about formal charges. Can these atoms be charged even if they're in a covalent compound? So I do want to say that these are the bonding rules for neutral atoms, or bonding rules, whoops, for neutral. And we're just going to go down the period 2, C, N, O, F. Neon already has a filled valence shell, so it doesn't require covalent bonding to add electrons to its octet count. So we're not going to do neon. They don't participate in any type of chemical covalent bonding. And we're going to do hydrogen as well. So neutral, C, N, O, F, and H. Let's do C first. Lewis dot symbol looks like this. The next column is going to be valence, number valence electrons, and we have 4. Okay. Based on our example here for this molecule, CH4, this is called methane, but you don't need to know the naming of covalent compounds in this case. We have 4 bonds. Our next column is bonds, and our last column is lone pairs, and there are 0. Our example is CH4, and we could, if we have space, draw an example. Carbon satisfies the octet rule. Okay, carbon satisfies the octet rule. In this case, nitrogen. I'll go through this a little bit faster, but look at your notes. How many bonds did nitrogen have when it's neutral? 3. Whoops, that's not the bonds. This column is the valence electrons. Okay. 5 valence electrons. How many bonds? There were 3 bonds. And how many lone pairs? There was 1 lone pair. Okay, we could redraw NH3 here. At this point, it doesn't matter the angle. It's called a bond angle, where you look at the angle between 2 bonds. It doesn't matter what the bond angle is. What's important is that you draw the right number of lines and the right number of dots. Oxygen. Oxygen we have not done. Oxygen has 6 valence electrons. And again, you could get the valence electrons from the electron configuration, just like we did for nitrogen over here. Okay. And we could arrange those 6 valence electrons like this. Okay, so keep that in mind. To figure out the bonds and lone pairs, again, I'm going to have the central atom, in this case oxygen, surrounded by enough hydrogens to give this 8 electrons. So we have 2 hydrogens because we're missing 2 electrons to reach the octet count. And then don't forget your lone pairs. Oxygen typically has 2 bonds and 1 lone pair. I gotta look at my drawing. 2 lone pairs. 2 lone pairs. Am I saying that you have to memorize this table? No, I'm saying that you can create this table based on these molecules, and eventually this table will be intuitive. That you will say that oxygen, when it's neutral, has 2 bonds and 2 lone pairs, right? Let's go to fluorines next on the periodic table. Yep, fluorine. Fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Let me zoom out a little bit. Again, let's take our element of choice and add enough hydrogens to see that the atom has 8 valence electrons. Or let's stop saying 8 valence electrons. Let's say that it satisfies the octet rule. All of these atoms, C, N, O, and F, right? They all satisfy the octet rule. And the way you count, let's do it for fluorine. 1, 2, 3, 4, 5, 6, and you count both electrons of the bond. 7, 8. So basically, to count, let me write it somewhere. To count if atom satisfies octet rule, what I like to say is you count all the electrons surrounding that atom, directly surrounding that atom. Count all electrons now. Remember that phrase. Now hydrogen is a little bit different because it only has 1 valence electron. Oh, we never finished the bonds and lone pairs for fluorine. We have 1 bond, 3 lone pairs. Last one is hydrogen. Hydrogen has 1 valence electron, but it doesn't need 8 electrons to fill its valence shell. Its valence shell is n equals 1. It only needs 2 electrons. This will be 1 bond and 0 lone pairs. And our example for that is just simply H2. H2. Okay, let me zoom out because that's basically the table that I want you to be comfortable with. Again, you'll find that you don't really need to memorize this. It will be natural when you start working with molecules that have carbon, nitrogen, oxygen, or fluorine. Okay? And you're going to make the bonding situation so that each of those atoms satisfies the octet rule.